So today, actually, don't think we'll have a super long class, which is good, so you'll have time to go home and smoke pot. But, you know, we do have some stuff to talk about. So this all comes under the heading of chemical accounting. You don't have to smoke pot when you go home. I was just saying that because that's what I'm going to do. What?
I said I like the encouragement.
Oh, okay, yeah. This roughly follows chapter 5 in your book, if you're going along with that, although, as with all the other chapters, they go into some more depth than we will. And I'm sorry for those of you who are not math fans, which I know that's only a couple of you, but we're going to be doing a little bit of math today. I know most of you are excited about that, so that's good. First part will be math, but just counting some numbers, and so hopefully that's okay. All right, we talk about chemical accounting. What we're really talking about is how chemical reactions work. All right. Now you've done a chemical reaction so far. I think just one, the biodiesel reaction. You're going to do another one next week, I believe, or the week after with the synthesis of the organic molecule. And the way chemical reactions work is you have some molecule, let's say hydrogen. We've talked about a hydrogen molecule, it looks like that. And you could react that with, let's say, an oxygen molecule. And if you react a hydrogen molecule with an oxygen molecule, you can make water. But there's a problem with how I've just drawn that. Can anybody see what the problem is here? Yeah, Joe.
I was going to say, like, when it says plus O, it would be a double bond.
Oh, that's right. That is one problem. Thank you. There was another one I was thinking of. Yeah, you're missing oxygen on the far side. So if this were actually how the reaction went, what this is telling us is that an atom of oxygen simply vanished. And why can't that happen? Do you remember?
Conservation. Yeah, I guess it would be.
Close, conservation of mass. Yeah, there's law of conservation of mass that says that in a chemical reaction, matter, stuff, can't be created or destroyed. Atoms are turned into other things, molecules are turned into other things, but you can never simply destroy matter. You can't take an atom, do a chemical reaction, and have that atom simply not exist anymore. That can't happen. Yet the reaction that we've drawn up here shows that happening. So what do we do instead? What happens here? Yeah, we could simply say that the oxygen is left alone, an oxygen atom. But what if I said this? Well, okay, I did this reaction, and I analyzed my products, and I didn't find any extra oxygen atoms around at the end. Is there a way that this works without extra oxygen atoms coming up at the end? Well, not exactly decomposition, but yeah, the reaction will happen in a slightly different way. So what we can say is, if we know that this actually isn't the case, which is true, what if instead we have two hydrogen molecules react with one oxygen molecule, and we make two water molecules at the end? Does that work? Is matter either created or destroyed in this scenario? It's not, right? We have 4 hydrogen atoms on the left and 4 hydrogen atoms on the right. So there's 4 hydrogen atoms here and 4 hydrogen atoms here. And we've got 2 oxygen atoms here and 2 oxygen atoms here. So then what this tells us is that hydrogen and oxygen have to react with each other in a 2-to-1 ratio, actually. in order for all the stuff to be used up properly. And the way we knew that is by changing the quantities of the molecules so that they were all balanced at the end. Now we express a reaction like this, not usually like this, where we draw out all these structures. We usually express it in something we call a chemical equation. Where we use the molecular formula rather than the molecular structure. And so we would draw this one as H2 plus O2 yields H2O. And that's called a chemical equation. And then to account for the fact that we need two of these and we end up with two of these, we put 2's in front of those symbols. Now where those go is important. The number, the little subscript number on the bottom, tells you how many atoms are within the same molecule. So like water is H2O, that means there's two hydrogen molecules, or two hydrogen atoms in the water molecule. The number out to the front, out left, is called the coefficient, and that tells you how many of the molecule you have. So the 2H2 means you have two hydrogen molecules, two separate molecules. And this equation is called balanced now because the mass is balanced on each side. And that's going to be now an important point of something that we can do, is we can balance these equations so that they do indeed have the correct mass on either side. Let's try one. Here's another chemical equation. This is a molecule called sodium azide, and it actually reacts by itself to become a sodium atom and nitrogen gas, N2. Now, is this equation, as it's written here, balanced? It's not. What's wrong with it? There's a nitrogen missing. So now I have to manipulate those coefficients, those numbers in front, in such a way that they do now balance. So let's do that. How do you want to do that? How can we do that? Yeah. Okay, yeah, great. So we've got 3 of these and 2 of these. We can't just add another, we can't just change this 2 to 3 because that changes what that molecule is, right? We can only mess with the numbers out in front. So we have a space here, we have space here, and we have space here. We can change those all we want to change the ratios. And the suggestion was to go 2 of these, which gives us now 6 nitrogen atoms overall. See that? And that means we need 3 of these to also have 6 nitrogen atoms. So like I said, a little bit of math, sorry. But 2 times 3, you could probably handle, right? Okay. Now is it balanced? No, because what happened? Right, when we put that 2 in, we changed the number of sodiums from 1 to 2. So now we have to put the 2 here to balance that out. Now is that one balanced? Yes. Okay, great. Here, try this one yourself. This is the smelting of iron ore. Oops. Where iron ore is mixed with carbon or coke to produce carbon dioxide and iron metal. See if you can balance that one on your own. Looks like a lot of people got it. What's out of balance here? The oxygen and the iron. We start with, we have 3 oxygens here, 2 iron, and 1 carbon on this side, and we have 2 oxygens, 1 iron, and 1 carbon on this side. So the oxygen and the iron are out of balance. And which one you do first or which one you try to balance first doesn't really matter in this case. In a reaction where there are multiple molecules with the same atom, you want to do those last because otherwise they affect each other and it gets really messy. But in this case, it doesn't matter. So what do you want to balance first, the oxygen or the iron? Oxygen, okay. So we've got 3 on the left and 2 on the right. How do we balance those out? Yeah, 2 and 3. So we end up with 6 here. If we put a 2 there, we now have 6 oxygen here. And that means we need a 3 there so that we have 6 here. So you always need to multiply the coefficient by the little subscript number to figure out how many total atoms you have. Okay, now what about the iron? Right, we've changed this now, so we've changed this to 4 on this side, which means we need 4 of them over here too. Okay, and now is the carbon still in balance? It's not because we changed this to 3. So what do we do over on the left? Yep, multiply by 3. And recheck it and everything should be in balance. The nice thing about doing these problems, even if you're just guessing and you just throw random numbers out there, you can always check your answer. You can always look at how many of each atom are on this side, how many of each atom are on this side. If they match up, you got it right. If they don't match up, you didn't get it right. So, you can go back and try again. So that way, it's nice. It's not like you have to kind of wait till you see the answer to check it.
They match up on the, I use like bigger numbers, like a 4.
Uh-huh.
Like 4, like for the iron, and like 6 for the carbon.
Mm-hmm.
They still like match up, but I just like,
So you did like this?
yeah.
Yeah. Yeah, that works too, right? That's balanced. Usually we use the smallest numbers that we can. So if you notice that all of your numbers can all be divided by something, you should do that. But that's a fine way to actually find the balance. Is if it's easier for you to use the bigger numbers in some cases, absolutely use them and then divide them down at the end so you come back with some of the smaller numbers. All right, let's try another. We'll start getting a little bit trickier. Just a little bit. This is what happens when calcium metal reacts with water. You produce calcium hydroxide plus H2. Now the difference, that's hydrogen gas. Now the difference in this case is the calcium hydroxide over on the right has these parentheses. What does that mean? That's right. So in that molecule, well, it's an ionic compound, but we'll call it a molecule, you have an atom of calcium and 2 ions of OH. So overall, you have 1 calcium atom, 2 oxygen atoms, and 2 hydrogen atoms. But again, you can't mess with those little numbers on the bottom. You can only mess with the numbers out front. So see if you can balance this one also. Only messing with the out front numbers. Again, it's always helpful if you do your accounting first. You just add up the numbers of atoms on each side. So you've got a calcium on this side, 1 calcium on this side. How many oxygen on this side? And how many on this side? 2. And how many hydrogen on this side? And how many on this side? Total 4, because 2 from here and 2 over here. All right. So out of balance then are the oxygen and the hydrogen. Now this is an example of where you probably want to balance the oxygen before the hydrogen. Why is that? Yeah, there's only 1 oxygen on either side. The hydrogen, you might affect other things that you might not want to. So let's do the oxygen first. We've got 1 on this side and 2 on this side. How do we get that balanced? we need one more. But remember, we can't just take one more atom. What we do affects the entire molecule. So we need to put a 2 out front here, and that affects the entire molecule. So let's revise our numbers now. On this side, we still have 1 calcium, but we now have 2 oxygen. And have we changed our hydrogen count too? We have, right? Because we now have 2 of these molecules. So we now have 4 hydrogen atoms. Okay, so what's out of balance now? Nothing, right? That's it. So now it's balanced. It's always good to recheck every time you make a change and revise your numbers, because sometimes you'll just do one simple thing and then everything will be good. Right? Okay, let's try another one. This one will be a little trickier still. This is what happens when that calcium hydroxide reacts with phosphoric acid. All right, before you start messing with this, take a look at the molecule all the way over on the left. That's calcium phosphate. How many oxygen atoms are in calcium phosphate? 8, right, because it has 2 of these phosphate ions in it, and each one of those has 4 oxygens. So total, we need to count that as 8. So don't be confused by that way of writing things. It just tells you how many of this and how many of this inside the parentheses. Again, make your counts and try to balance that out. This one was the trickiest one yet because there's a lot of stuff to deal with, a lot of stuff to keep track of. Let's first get our tallies down. On this side, I've got 1 calcium, 1 phosphorus. How many oxygen here? We've got 2 and 4 is 6. And then 5 hydrogen, right? Does that look like the tallies you got? So that's just counting up the atoms. Okay, that'll do it. And then let's check the other side. We've got 3 calcium. We have 2 phosphorus, because there's 2 of these things in the parentheses. Then we've got 1 plus 8 is 9 oxygen and 2 hydrogen. Look like your tallies? Mostly? Okay. So that's the first step to doing these right, is actually counting everything up properly. And it can get tricky, especially with these parentheses and extra ions, so make sure you're accounting for everything. All right, what do we not want to balance first? Yeah, probably hydrogen and oxygen, because they exist in multiple molecules. So if you try, like, for instance, oxygen is in every molecule. So if you tried to balance something over here, you know, it's 6 and 9. So how do you know if you want to add 3 to this one or add over here? You don't really. So that's not a good way to start. Start with ones where they only exist in one molecule or the other. So let's start with either calcium or phosphorus. If we start with calcium, there's 1 over here and 3 over here. So we could balance that by putting a 3 there. Now let's update our tally. We now have 3 calcium over here. We don't have 6 oxygen anymore, because now we have 2 per calcium hydroxide and then 3 of those. So that's 6 in this molecule, and 4 in this molecule is 10. And now with hydrogens also, we've affected that. So we've got 6 in this molecule and 3 over here. That's 9. Right? Yeah. Okay. So what should we balance now? Phosphorus? Sure. We've got 2 over here and 1 over here. So how do we balance that? 2 here. Now I saw several people put the 2 like in between the hydrogen and the phosphorus. That doesn't work. these molecules are 1 unit, and you can only change the amount of the whole thing. So you have to put the number out front. And that changes our tallies again. Now we have the 2 phosphorus, so that works out. But we've also changed the number of oxygen from 10 to what, 14? And the number of hydrogen from 9 to, there's 6 here now and 6 here, which is 12. Right? Okay. So now let's start looking at those. We'll look at the hydrogen first, because again, it's not in as many atoms, or not in as many molecules. We have 12 on this side and 2 over here, so how do we balance that? Yeah, we're going to need 6 of these. And then that's going to change our oxygen count too. So that's moved this to 12, and that's changed our oxygen count to 6 plus 8, which is 14. Is everything balanced now? It is. So by going systematically and keeping track of our counts the whole way, we were able to get it balanced. All right, one more, and then we will start talking about why this is important and what it means. So I'm going to take tin reacting with sulfuric acid. Will give us tin sulfate, sulfur dioxide, and water. Okay, give this one a try. Good. All right, let's get our accounts down first. A couple people asked about the SN versus the S. Do the S's go together because they're both S's or not? In fact, they don't, because SN and S are different types of atoms. They're different elements. S, sulfur, number 16. SN, tin, number 15, number 50. So watch those. I know it can be confusing, but if there's a lowercase letter to the right of it, that's an element. All the element symbols are either just one letter or 2. So you can watch for that to try to figure that out. So on this side we've got 1 tin, 1 sulfur, 4 oxygen, and 2 hydrogen. All right. On this side we've got 1 tin. We have 2 sulfur because there's 1 in this molecule and 1 in this molecule. There are, let's see, 4, 2, and 1 is 7 oxygen and 2 hydrogen. All right. So what do you want to balance first? Probably the sulfur, right? It's in fewer molecules. So how do you balance the sulfur? Right, there's 2 on this side and 1 on this side. This is the only molecule on the left with sulfur in it. So we need a 2 here. So we have 2 of them. Now let's correct our counts so we don't get screwed up with other stuff. We now have 2 sulfur. We now have 8 oxygen. And we now have 4 hydrogen. Okay. So the tin and sulfur are balanced. The oxygen and the hydrogen are out of whack. Which one do you want to balance next? Right. So now instead we're going to balance hydrogen because it's only in 1 molecule over here. If we tried to balance the oxygen, how would we know if we have to increase this one, or this one? We wouldn't. So we do the hydrogen because there's only 1 possible molecule that we can mess with. And that's this one. Right now we have 2. We need 4. So that means we need to change that from 1 to 2. Okay, and then let's update the counts. That gives us 4 hydrogen and 8 oxygen. So we're done, right? That's it. Okay, great. All right, we'll take a little break, about 15 minutes. We'll come back and talk about why this is important and how to do some further calculations with it. If you're struggling with this, or if these exercises are really difficult for you, that's fine. This is new. You're not supposed to get it right now. But make sure that you make that a priority to review this and work on it on your own before next week. All right, so looking at these things that we just talked about, we did this whole exercise of balancing. But it's not just an exercise. It's not like I care, that we can do these numbers right or something. It has real physical importance. And the physical importance is, if we go all the way back up to our original example, the hydrogen and oxygen, if you have a certain amount of oxygen, let's say, you need a certain amount of hydrogen to react with it. And if you're planning to do a chemical reaction, as you will do throughout the semester, you need to know how much of this to measure out and how much of this to measure out. And that equivalence has to do with the individual molecules. So each individual molecule of oxygen needs 2 molecules of hydrogen, or else that reaction won't go efficiently. You won't get it. So ideally, we would take our tiny molecule tweezers and pick out 2 molecules of hydrogen for every 1 molecule of oxygen that we pick out. Of course, that's not physically possible because we can't pick out individual molecules. They're just too small. So how do we count this to actually make this work? Anybody know?
Multiply for hydrogen, take the 1.00794, multiply that.
Yeah, but like we'll get to that in a minute. But in a more general sense, we do it by weighing. When we count our reagents for a chemical reaction, we don't count the individual molecules. We weigh them out on a balance. And that mass has some relationship to the number of molecules. But unfortunately, it's not exact. So if we know we want, or exact isn't the right word, it's not correlated in that way. If we want 2 molecules of hydrogen for every 1 of oxygen, that doesn't mean we can take 2 grams of hydrogen and 1 gram of oxygen. Because oxygen's a lot heavier than hydrogen. It has more protons and more neutrons and electrons. So we have to account for that somehow. And we do that, the way that we do that is what we say is counting by weighing. Did I spell it right? Counting by weighing. So if something's too small for you to physically count it, or it's just impractical to physically count it, you can weigh it assuming you know how much one of those particles actually weighs. And that's what the M&Ms are for now. So that equivalence in molecules is something called the mole. The mole is a set number that we apply to atoms. And it's a huge number because atoms are so small. The number is 6.02 times 10 to the 23rd. So it's an enormous, enormous number. Remember, a million is 10 to the 6th, a billion is 10 to the 9th, a trillion is 10 to the 12th. This is 10 to the 23rd. So it's almost an unimaginably large number. And it's not any kind of unit or measurement. It's simply a number. It's like a dozen, right? If you say you have a dozen of something, it means you have 12. If you haven't heard of that, that's a dozen. It means 12, right? If you have a dozen of something, you have 12. If you have a mole of something, you have that many. Okay? It's essentially the same thing. It's just a name that we give to one particular number, and it happens to be that quantity. A mole of baseballs would be about the mass of the Earth. Okay? So huge, huge number. Huge number. A mole of drops of water, which are, small, is about the amount of water in all the oceans. So again, this is only a useful number when dealing with incredibly small things like atoms and molecules. But this is how it's useful. 1 mole of carbon, which equals, so that's going to equal 6.02 times 10 to the 23rd atoms of carbon. And that equals 12.011 grams of carbon. And that's the important part here. Where does that 12.011 number come from? The table. If you look at C, element 6, you see it says 12.011 underneath it. So that number tells us the average mass of 1 mole of that substance. So we could never count 6.02 times 10 to the 23rd atoms of carbon. Even if we could pick them up, and we do have technologies now that can pick up individual atoms and move them around, we could not do that many times. It just would not be physically possible. So if we want to measure a certain amount of carbon, the only tool we really have is the balance, and that's how we do it. We can weigh out exactly 12.011 grams of carbon and be confident that in that sample includes that many atoms. And that's how we can do these ratios with the equations. It's the same thing with molecules. If we go back up here, say we want to do this reaction, and we want 2 sulfuric acids for every 1 tin. We can't count them out individually, but we can measure out a mole of tin and 2 moles of sulfuric acid. And that's how we would do this. So let's talk about how the mole works in a chemical context. Let's take that reaction that we did initially. We have 2 hydrogens plus oxygen gives water. Well, let's say we want to do this reaction. We can't count out molecules of hydrogen, we can't count out molecules of oxygen, but we can count out a mole, or we can weigh out a mole of hydrogen and a mole of oxygen, or 2 moles of hydrogen and 1 mole of oxygen. But we have to figure out how much that would weigh. So let's try it. How do we figure out 1 mole of oxygen, and now we're talking about O2, not just O. How do we figure out how much that weighs? Yeah, you have to add up all the masses of the individual atoms in your compound or in your molecule. So there are two oxygen atoms in an oxygen molecule. Each oxygen atom is about 16. Yeah, so each mole of oxygen is going to be 2 times 16 grams, or about 32 grams. What about hydrogen? Let's start with 1 mole of hydrogen H2. That's going to be 2 times about 1 gram, right? Hydrogen's about 1 gram each, or about 2 grams. But we need, for this reaction, we need 2 moles of hydrogen, which is going to be 4 grams. So we can't pick out individual molecules, but if we weigh out 4 grams of hydrogen and 32 grams of oxygen, we know that we have the proper 2-to-1 ratio. We know that for every single molecule of oxygen, there are going to be 2 molecules of hydrogen in that sample. And that's how we do chemical calculations. That's how we figure these things out. We use this mass relationship, figuring out how much each one weighs, or each mole weighs, and then converting that. So let's practice this a little bit and see how we do it. Let's take sulfuric acid, H2SO4. That quantity, the amount of mass in 1 mole, is known as the molar mass. And the molar mass equals the mass in grams of 1 mole. It's also, you may hear it referred to as the molecular weight or molecular mass, or the formula weight. These all mean the same thing. Molar mass, molecular weight, formula mass. So the mass of 1 mole. So calculate the molar mass of sulfuric acid by adding up the molar masses of each atom, multiplying them by the quantity of each atom in the molecule. And don't use too many decimal places. Let's just round them off and say we're just going to use the whole numbers for now. Is what? 90? 98. And the unit here is grams per 1 mole. So that means there are 98 grams in 1 mole of sulfuric acid. If we want 1 mole of sulfuric acid, we have to measure out 98 grams of it. And then we know we have exactly that number of molecules, that big number of molecules. All right. This conversion is very important because we have to keep doing it whenever we're doing chemical reactions. We have to keep going back and forth between moles and grams. So what happens if you have, let's say, 150 grams of sulfuric acid? How many moles do you have? How do you figure that out? Yeah, you're going to divide it by the molar mass. Or another way of expressing this is to say we'll take 150 grams and multiply it by the conversion factor that tells us that there are 98 grams in 1 mole. So the grams on the top and the bottom here will cancel, and we're left with moles. So we want to do that calculation. So this was the math part I was talking about. 1 point what?
5.3.
Okay. And the abbreviation for moles is not very abbreviated. It's MOL instead of MOLES. They kind of had to do that because M is meters and MO is months, and so the next one is MOL. So that tells us, doing that calculation tells us that we have 1.53 moles of sulfuric acid in a sample of 150 grams. So let's go back up to that equation. This one here. I'm going to rewrite it down here. Remember this equation? Tin plus 2 sulfuric acid gave us tin sulfate plus SO2 plus 2 water. That was a 1, right? Yeah. So remember that equation? Okay. So now let's say we have this 150 grams of sulfuric acid, and we want to know how much tin we need to add there. So if we have 1.53 moles of this, how much tin in moles do we need? And how do you know that? And how do you figure it out? Any idea? Well, don't get too far ahead of us there. Let's look at the equation. The equation, those coefficients we came up with in the balancing, are so important because they told us that we need 2 molecules of sulfuric acid for every 1 of tin, which also means we need 2 moles of sulfuric acid for every 1 mole of tin. So if we have 1.53 moles of sulfuric acid, how many moles of tin would we need? Or, I mean, if you don't have an exact number, how many in relatively? Yeah, you need half of it, right? What these two numbers tell us and this is actually a 1, even though it's not written, is that those molecules always react in a 1 to 2 ratio. 1 tin to 2 sulfuric acids. 1 to 2, 1 to 2. So if what we have is 1.3, what we need here to react exactly the same is half of that. Half of 1.53 is about 0.76, right? So if we want to do this reaction and have everything matched up properly, we need 0.76 moles of tin and 1.53 moles of sulfuric acid. All right, next question then. If we have 1.53 moles of sulfuric acid, how much water will we form? What's the equivalence there? What's the ratio? What? It's 1 to 1 with sulfuric acid, or it's double with tin. And this is why the mole thing is useful, because we don't have to care about those masses anymore. Once we have the moles, they all keep the same equivalence. So if we start with 2 molecules of sulfuric acid, we end with 2 molecules of water. If we start with 1.53 molecules of sulfuric acid, we end with 1.53 molecules of water. And we can always substitute that term mole, which is like saying molecule but times a bunch. Right? So if we start with this, that means we end with 1.53 moles of water. And what about SO2? How many moles of that do we end up with? 0.76. Because you started with 1 of these, you end up with 1 of these. Or you start with 2 of these, you end up with 1 of these. That's what the equation tells us. And what about tin sulfate? Also 0.76. So now we know in moles how much of this stuff we actually need. So let's go backwards then. How much water in grams is produced? So to figure that out, we take the number of moles of water and convert it back to grams. We know we produce 1.53 moles of water. So we're going to multiply that by the molecular weight, or the molar mass, of water, which is 18 grams per 1 mole. 1 oxygen is 16. 2 hydrogens, 1 each, that's 18. And that comes out to something like 27-ish, right? 27. So think about what we just did here. We took a certain amount of starting material and we figured out how much product we're going to get. But the only way we could do that is by first converting to moles and then going back to grams at the end. Because we need to be in moles to figure out those equivalences in red of how much each thing is going to make. All right, let's try some more. Here's another reaction. Whoops. I'll leave it like that. We need to balance this first, because it's not balanced. That's always going to be your first thing. Whenever you see a chemical equation, you should always check to see if it's balanced. And if it's not, balance it. So what's out of balance here? The oxygen. How do you balance that? So you're going to put 2 where? Yeah, you actually need it in a couple spots, right? You need 2 here and 2 here. Now it should be balanced, right? Okay. Before we start messing with the masses, let's just think about the moles. If I have 1 mole of NO, nitrogen monoxide or nitric oxide, how many moles of oxygen do I need to react with it? If I have 1 mole of NO, how many moles of O2 do I need? 0.5, right? Because they're in a 2-to-1 ratio. So you always need half the amount of oxygen that you have in NO, in nitric oxide. And this produces how many moles of NO2? 1, right? Because it's the same number of molecules that you started with. If you started with 2 molecules of NO, you produce 2 molecules of NO2. That's what the balanced equation tells us. And that's why it's so important to have a balanced equation. If that weren't balanced, then we'd get different numbers and they wouldn't be right. Now let's start playing with the masses. So I want to know if I start with 20 grams of NO, how much oxygen do I need? And how much nitrogen dioxide do I make? So this problem requires a couple steps. First of all, notice that we're in grams, so we can't do anything while we're in grams because these equivalences are all based on molecules or moles. So our first step is always going to be convert the initial amount in grams to moles. So step 1, convert 20 grams NO to moles using the molar mass, or the molecular weight. See if you can do that. If you don't have a calculator, ask someone else at your table to do the calculation, but see if you can set it up. Or if you have one of these cool portable telephones that you can carry in your pocket, sometimes they have calculators on them. You can use that. All right, let's go over this. So we're going to use the same procedure that we did earlier. We say, first of all, the molar mass, or the molecular weight of NO, is going to be nitrogen, which is 14, plus oxygen, which is 16. And that's 30 grams per mole. So each mole of NO has 30 grams. And then we need to say, okay, then 20 grams NO times 30 grams in a mole equals about 1/3, right? We'll say is that something like what you got? Similar? Close? All right. Now we know how many moles of NO we started with. We didn't start with 2, which is what the equation says. We didn't start with 1, which was what our little practice thing above says. We start with 0.667. So then how many, in step 2, how much oxygen is needed in moles. How do you figure that out? Right. We need half the amount of oxygen as we do NO in terms of moles. And we can actually set that up as a more formal equivalence also. We can say 0.667 moles NO times a ratio of 1 mole of oxygen per 2 moles of NO. And just like the other conversion above, you get the thing you don't want to cancel. So that's effectively dividing by 2 or multiplying by 1/2. And that means that we need to start with 1/3 of a mole of O2, 0.33 moles of O2. And then we can convert that to grams to answer that first question. Because we can't weigh out the O2 in moles, we have to weigh it out in grams. So 3 how do we take that 0.333 moles and turn it into grams? Right, we're going to multiply it by the molar mass. So we take 0.333 moles of oxygen and multiply it by how many grams per mole? 32. Each oxygen is 16. There's 2 of them, so 32 per molecule. And that gets us like 10.6, 10.7-ish. I think. So that means that answers our first question. We need to weigh out 10.7 grams of oxygen to react with our initial 20 grams of NO. And the only way we could find that is through the moles. All right. So then to get the next question, we need to figure out how many moles of NO2 we make and then convert that to grams. So using the same procedure as 2 and 3, we're going to do this again for the second question. Without me directing you through that, see if you can do that and come up with a final mass of NO2 in moles that you would make. Let's look at it the long way first. But we do the same thing, and we first figure out how much NO2 is made in moles using that equivalence. If we started with 0.667 moles of NO, how much NO2 do we end up with? The same amount, because there's a 1-to-1 ratio. 2 of these make 2 of these, so 0.6 of these make 0.6 of these. Okay? So then the last part is to convert it to grams. So we're going to take 0.667 moles of NO2 multiplied by the molar mass of NO2, which is 14 plus 16 plus 16, 1 nitrogen and 2 oxygens, 46 grams per 1 mole. And you end up with 30.7 grams. So that's the answer to this final question. What's the shortcut? Anybody get that? In this case, there's actually a way to solve this without going through those calculations. It has to do with the law of conservation of mass. We talked about initially, no mass can be created or destroyed in a reaction, right? So if we started with 20 grams of this, and the first part we calculated we need 10.7 grams of this, if we can't destroy or create any mass, then we must have to end with those added up, which is 30.7, which is actually what comes out when you do the calculation also. So that idea of conservation of mass is a good way to check yourself in these types of problems, because the masses that you use on both sides have to add up, or they have to equal each other. The left side and the right side have to ultimately equal each other. Okay. We'll try one more, and then we'll call it a day. Here's a reaction of the burning of hydrogen sulfide, which is a stinky thing. And I left a little room here so you can balance it. So balance that equation, and then say, we're going to do the reversed one here. Uh-oh. We're going to say we want 10 grams of sulfur dioxide. How much of the hydrogen sulfide and the oxygen do we need to put in to get that? How many moles did you come up with as the SO2? Did other people get a similar number? Or no? All right, let's try that. That seems like a bigger consensus. 1, 5, 6. Does that sound more right? Okay. One question that usually comes up with this, or sometimes comes up with this, do you use the coefficient when you calculate the molar mass? And you don't. The molar mass is always the same for a given chemical. So SO2 has a molar mass of 32 plus 16 plus 16. Doesn't matter how many of them are used in a given equation. So we wouldn't use that here. All right, so if we do have 1.156 moles, then how many moles of H2S do we start with? The same amount, because it's a 1-to-1 ratio. And what about O2? How'd you figure that out? Yeah, you have to kind of set up a proportion there. Or you can think of it as a conversion also. If you have 1.156 moles, let's say SO2, times 3 moles of O2 for every 2 moles of SO2. That's the conversion you would set up, so that the moles of SO2 cancel, and you end up with moles of O2. And what does that come out to? Anybody do that? No? It's like 0.2 something. Is that right? Okay. So now we've used those equivalents to find out the amount of moles we need for each. And then to figure out grams, we go back and multiply by the molar masses of H2S and O2. So if you multiply this by molar mass of H2S, which is 34, 32 plus 1 plus 1, what do you get? What is it? 5.3. And then over here, we'd multiply 0.234 times the mass of O2, which is 16 plus 16, or 32. $7.4. Okay. So now we have an idea of if we want to make 10 grams of SO2, we need to start with 5.3 grams of H2S and 7.4 grams of O2. Okay, that's